Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Lecture 5 of Dynamic Atomic Force Microscopy Methods. In the last few lectures, we've been focusing a lot on the exact and accurate point mass models of the AFM probes, the idea being that we really measure forces in AFM through the measured probe dynamics, so we really need to have a good model of the AFM probe in order to be able to convert what we observe, which is the motion of the cantilever, into the forces, which is where the real physics of atomic force microscopy lies. Now, the way we approached this was through a very self-consistent and mathematically accurate description using energy equivalence and using experimental methods such as the measurement of the thermal fluctuations of a cantilever and the use of both the equipartition of energy as well as the fluctuation dissipation theorem to try and measure the correct equivalent spring constant of a cantilever, the correct equivalent mass of a cantilever, and the Q factor. But also, in the past few lectures, we've really stressed the fact that one needs to model the excitation of the cantilever very well as well. And the excitation of the cantilever, whether it's from ditho-piezo excitation or magnetic excitation, leads to a certain expression in the point mass oscillating models. They either appear as an external force, oscillating force, F naught, in the case of directly excited cantilevers, or in the case of base excited cantilevers, it appears as a base motion in the point mass oscillator model. The nice thing is when one goes through this process of experimental thermal calibration methods, one is able to get all these effective properties that allow us to model the probe motion very accurately when compared to the real probe dynamics. What we are going to focus on today is, now we've got our point mass oscillator model with the excitation all worked out, we have to now start taking this model and getting it to interact with the tip-sample interaction forces. So we are now getting back into the physics of tip-sample interaction forces. And in this lecture, really what I want to do is to highlight some key features. It's going to be a brief review of many of the tip-sample interaction force models that you've studied in part 1 of the class. The first concept I'd like to review with you is the concept of a conservative tip-sample interaction force. What you see on the left is a figure of this point mass oscillator model. It could have some external forcing, F external, or it could have some base motion, Z base motion. But the key notation, the quantities here are FTS, which is the tip-sample interaction force, between a few group of atoms on the tip and a few group of atoms on the surface. We have the gap D. This gap D is the gap between the lowermost atoms on the tip and the uppermost atoms on the surface. Z is effectively the distance that's controlled by the motion of the sample or the Z piezo actuator or the motion of the base of the cantilever. And it basically measures the distance between the tip and the sample when the tip is not deflected. And Q is the actual additional displacement of the tip due to the interaction forces, so that D, the gap, becomes the sum of Z and Q. Now, when one is going through a dynamic AFM setup, one is trying to drive the drive the probe at a steady state oscillation, and one applies an excitation frequency omega, which is close to omega naught, the drive frequency. So the probe responds always at the excitation frequency. When the excitation frequency lines up with the natural frequency omega naught, then the amplitude becomes large and the phase reaches a certain critical value. The key thing is that when one looks at these kind of periodic motions of the tip as it oscillates in the presence of a tip sample in a small gap, one can think of the tip sample interaction forces, one can ask the question rather, are the tip sample interaction forces conservative or not conservative? What does a conservative tip sample interaction force mean? A conservative interaction force is one where when the tip goes through a cycle of oscillation, if the work done by the tip sample interaction force is 0, in one cycle, as the tip goes up and down and goes back, then it is a conservative interaction force. And you may recall from basic physics that such forces are described by their dependence on only the position of the particle. And so happens in this case that whenever there's an interaction force that depends only on the gap d and not on the velocity or the direction in which it's moving, but just on d, the gap at any instant, no matter whether it's moving away from the sample or coming towards the sample, whenever there's such a force, that force must necessarily be conservative in nature. We show in the next slide some examples that you may have come across already in part 1. The first is a linear spring contact model. This is if you were to model the sample as another spring, in this case with a spring constant K REP, super REP, for whenever the gap d is less than 0. So remember, when the gap d is less than 0, you're in contact and you're indenting the sample. And when gap d is greater than 0, there's a separation between the tip and the sample. So in this case, there is no force. The force is 0 until the gap becomes 0, and then you press in and there's an indentation, and the force increases linearly as a function of the indentation. This kind of a simple interaction model is conservative because it depends only on d, the tip sample gap or the tip position relative to the surface of the sample. So when one goes in and goes out, the force is going to follow the same trajectory. It's not going to have a different value because the force just depends on the position, d, of the tip, not whether it's going in or going out of the sample. The second example at the bottom is a Hertz contact model. This is again a contact mechanics model that you've studied in part 1, and it really models the elastic indentation of a sphere into a half plane, elastic half plane, and it prescribes the tip sample interaction force to be 0 before contact occurs. And when contact occurs, you get this repulsion that's described by the contact mechanics or continuum theories of contact mechanics, where the sample wants to push the tip out. And this is given by a characteristic 3/2 dependence, power law dependence on the indentation. Remember, d is the gap, so negative d becomes the indentation into the sample. Where E star here is this quantity that has been discussed before in part 1, which is the effective modulus of the tip sample combination. So in this case also, this is a tip sample interaction force, which is conservative because it just depends on d, no matter whether you're going in or out of the sample. So if you were to measure tip sample interaction force in a hypothetical experiment as a function of d, if the gap between the tip and the sample were reduced and moved away, one would go in and come out along the same curve. Another example that you studied in part 1 was the DMT contact mechanics model, which included Van der Waals forces in the description of the tip sample interaction forces. So in this case, you had this negative force that was increasing as you approach the sample. At a certain point, the force starts becoming repulsive. Through the mathematical description as shown out here, when you're far from a sample, you have Van der Waals forces. Van der Waals forces between a sphere and a flat sample do go by the inverse distance square law, which again means that it's a conservative force because it does not depend on the direction in which you're moving. It just depends on the position d of the tip relative to the sample. So this would also be a conservative interaction force. And the repulsive part is also conservative because it depends only on the displacement or only on the position of the tip d with respect to the sample surface. Now, the reason I bring up this DMT contact mechanics model is just to remind you that you could take this conservative interaction model and try to understand what is the force versus z that you might get with an AFM. You could do a thought experiment where you could actually put a cantilever and see what happens to the force measured by the cantilever as a function of z the motion of the base of the cantilever. And if the cantilever is soft enough, you've discussed this in part 1, that even in this conservative interaction force model, you could get the cantilever snapping in and pulling out of the substrate. So in other words, you might get a hysteresis in the F versus Z graph, even though the F versus D graph, as shown here, has no hysteresis and is perfectly conservative. And this is one of the key shortcomings of static atomic force microscopy methods, that they're unable to distinguish between snap in and pull out that happens due to conservative interaction force, where the attractive force gradients overwhelm the cantilever stiffness and the cantilever snaps in and pulls out, as opposed to a true hysteretic tip sample interaction force that we'll talk about shortly. So in contrast to a conservative interaction force model, we have non-conservative tip sample interaction forces. Non-conservative forces don't just depend on the tip position, d, relative to the surface, but they also depend on the velocity of the tip, whether the tip is approaching the sample or moving away from the sample. And in this case, when you go through a cycle of tip motion, when the tip goes through a cyclical motion, Q or D as a function of time going through a cycle, then the work done by the tip sample interaction force, FTS, on the probe, which is the cyclic integral shown here, is no longer zero. It'll be non-zero, representing the work done by the force on the probe, which is, you can also put a negative sign and regard this as the work done by the probe on the sample as well. Let me give you some examples that you have already seen through part 1 for non-conservative interaction forces. The first being the JKR contact mechanics model. Now, the JKR contact mechanics model really, as you discussed in part 1, is valid when you have tip sample contact between a compliant sample and a highly adhesive and compliant sample. What happens in that case is that as the tip comes close to the sample, the sample itself can actually deform a neck due to the low elasticity and high adhesive forces, which require the tip to move and break this bond effectively. And this is different from the cantilever snap-in and pull-off. So what ends up happening here, as you see on the top right, is the tip would approach the sample along the red line, and when it reaches contact, one suddenly develops a negative attraction force and goes in following a Hertz contact model. So when one comes out following the green line, one has to really move out further to a larger gap. In effect, the neck formed due to the very soft material as it wicks up effectively, holding on to the tip. You have to move the tip to a larger gap before it actually breaks ruptures this neck that forms. And that rupture happens along the green curve shown there. So what would happen is, when you go through a cycle of motion, the interaction force history, FTS, is different when you approach the sample, when you move away from the sample. And so this is an example of a non-conservative interaction force. Another typical example is shown in the second figure on the right, which is viscoelasticity. So what ends up happening in this case is, when the tip comes in, presses into the sample, typically polymeric samples, there is viscoelasticity in that as you press on the sample, there's a relaxation associated with the material, in that you're applying a strain to the sample, but the stress doesn't develop at the same rate. So as a result, when one goes in and comes out, there's a hysteresis in that force versus D, indentation in this case, follows a certain direction when you approach the sample and follows a different direction when you come out from the sample. In this case, again, a hysteresis loop is formed in the F versus D, and the force now depends on whether you're approaching the sample or indenting while approaching the sample, as opposed to coming out of the sample or retracting from the sample. Another example of a non-conservative interaction model are capillary forces, which are also you've studied. And these happen due to the fact that when one does AFM experiments under ambient conditions, there's always some relative humidity around, and as the tip comes close to the sample, in the narrow gap between the tip and the sample, these water molecules condense, forming a little neck, meniscus, if you will, and that has to be broken off as the tip separates from the sample. And that's again shown in the figure, where you see the tip approaches the sample along the red curve following a certain force, attractive force, but when contact occurs, suddenly a liquid neck forms and the force jumps to a lower value, representing the additional force applied by the capillary as it suddenly forms and is pulling the tip into the sample. And then one goes further into the sample, one follows a Hertz-like law from that point onwards. However, when one pulls away, one follows the green line, and the green dashed line represents the part where one is pulling away and stretching this liquid neck, and finally, until it finally breaks at a certain gap D0, as shown in this figure. So this again would represent a non-conservative tip-sample interaction force model, in that there's a net loss in energy from the tip to the sample. As you come in and move away from the sample, there's an energy lost in the whole process. So these are all examples of non-conservative interaction forces. So if I were to ask you a simple question, if you're doing an experiment, a dynamic AFM experiment, what kind of tip-sample interaction forces are you going to encounter? And the answer is going to be non-conservative. In effectively every case, there's always some source of dissipation, some force that makes sure that the tip-sample interaction forces are not just depending on position, but also dependent on velocity. And what we do in dynamic atomic force microscopy is we use a very common decomposition of these interaction forces, which I'll try to illustrate on the board right now. So if I went on to the board and try to sketch this out for you. So we have along this axis the tip sample gap D, and we have the tip sample interaction force FTS along this axis. As one approaches the sample, one might approach along this direction. When one moves away from the sample, one might approach or retract from the sample along that direction. This area represents effectively the work done by the tip sample interaction force on the tip motion. So that means in one cycle of oscillation, as the tip comes in and moves away from the sample, the net work done is no longer zero. Now, what we often do in dynamic atomic force microscopy is split this tip sample interaction force into two components additively. The first component would be the conservative part, where what we do is at every D value, we take the average value of the force during approach and during retraction, which I show by the dotted line here. Plus whatever else I need to add on to recreate this force. So I would rewrite this as the sum of a force that does this, following the average value, the average of the force between the approach curve and the retraction curve, plus whatever remains would be a purely hysteretic loop that does this. So in other words, I have done a decomposition of the actual tip sample interaction force physics into a tip sample interaction force, which is conservative, shown by the dotted line here, and to another one which is purely dissipative, which is shown here. Now you may well ask, is there a physical meaning to such a conservative force or to such a dissipative force, which I have come up with here? And the answer is not necessarily. This is a mathematical description that allows us to break the actual measured forces into a part which depends only on the gap D, and another part that is purely dissipative. And so with this, we will conclude this lecture where we have focused on the differences between conservative and non-conservative interaction forces and the decomposition of real forces encountered in an AFM in an additive manner where we write them as a sum of two components, one being the conservative part, which is the sum of the force you would get during approach and during retraction at the same gap D, and the other, which would be the remaining part, which comes from isolating the difference between the force encountered during the approach and the retraction curves. Thank you.